In this video, we'll go through the final components of crashing for networks. So looking at our notes where we're starting to look at reducing multiple activities. So when we're allowed to crash, sometimes we are actually allowed to reduce by more than just the one activity. So for instance, we have a school library being built, separate stages requiring for the construction, number of weeks taken shown on the network below. Often there'll be a few questions asked to sort of lead you in, but then this question comes down to if stage A was reduced by 2 weeks and stage F also reduced by 2 weeks, what would be the new critical path and the new minimum time? So this is what we would refer to as crashing with no cost, no restrictions. So they're giving us specific times to reduce the activities by, but we're not held to any budget. Okay, we don't have a target to reach. It's just do everything you can in order to get the minimum completion time, so the overall maximum saving. But firstly, let's go through and answer the questions that are there. So we're asked to find the earliest start time of F, what is the minimum time taken to build the library, and so on. So in order to do that, we're going to need to do our forward and backward scanning. So despite crashing not necessarily needing this, we do need it for the forward and backward scan. So just a quick refresher on that. Remember, we're drawing boxes at each of our vertices so that we can note our earliest and latest start times. And then our forward scan, starting at 0, and A would give us 3, G plus 6 would be 9, H plus 3, 12. But remember, we must consider all pathways coming in. So go back to the start. B gives us 3, but from activity E, 3 plus 2, 5, and we take the largest value moving forward because F cannot start until both E and B have finished. So the longest pathway is what we move forward with. So then F, 5 plus 5, 10. And let's go back and do C and D. So C, 5 plus D, 4 is 9. Largest number is 10. I is 5, so 10 and 5, 15. So that means our finish time, 15. Working backwards from there, so 15, our backward scan, so 15 minus H gives us 12. 12 minus 6 is 6. Remember, we must also consider all paths coming back into that vertex. So going back to the finish at 15, 15 minus 5 for I, 10. 10 minus 5 for F, 5. And then 5 minus 2 for E would be 3. Smallest value working backwards. So 3 in the box. And that means A would have a later start time of 0. B, so 5 minus 3 would have a later start time of 2. And then the path C, D, so 10 minus 4, 6. 6 minus 5, 1. So 0 goes in our box. So our critical path here, A, E, F, and I. Okay, remember you're following the edge that has the value, the red number, that went into the box. So first question there is, what is the earliest start time of F? So F, earliest start time, 5. What is the minimum time that it will take to build the library? That's our finish time, so 15. What is the critical path? So we highlighted that, A, E, F, I. And what is the float time for stage H? So H, remember your float time is your earliest start time minus your latest start time. So in this case, latest start time minus your earliest start time, 12 minus 9, 3. Part E, if the overall time of the project was to be reduced, which stages would reduce the overall completion time if shortened in isolation? So if I can only reduce one activity and I want it to have an impact, it has to be something on the critical path. So which stages we would reduce A, E, F, or I. Okay, so any one of those in isolation would have an impact. For part F, so here's where we're reducing multiple activities. They're telling us to reduce stage A by 2 weeks and F by 2 weeks. What would be the new critical path and the new minimum time to complete the library? So here you have the option of either. So one option is to write the new completion times on the network and check new forward scan. Okay, that's one option. Option 2 is to use the table method, which means you have to find all of the paths and then reduce both A and F by 2. In this case, I think it's actually much quicker to do it straight onto the graph with option 1. So that's what I'm going to do. So what that means is back on my network, activity A is now only going to take 1 week because I've reduced it by 2. And activity F is now only taking 3 because that, again, reduced by 2. So it might help to just do a bit of a cleanup so that we can see what we're doing. And often you might be given a separate or a second version of the graph that you can edit so that you can do this. So now our new forward scan. So A will give us 1, G 7, H would bring us to 10. E, let's follow through that. So 1 plus 2, 3, whereas B also 3. 3 plus F, 3 is now 6. Through C, 5. D is 9. So 9 is what we have to move forward with. And then 9 plus 5, 14. So our new finish time would be 14 weeks with both of those activities reduced. And so you can see there, even though we actually cut 4 weeks in total in time from the activities in the network, so from those stages, we ended up only saving 1 week. Okay, the original overall completion time or minimum time is 15, and we got it down to 14 weeks. So the next layer, the next style of question you might then be asked is, well, what if you didn't want to just waste money and resources and you actually wanted to ensure that you were only reducing what you needed to reduce? And that tends to be where we come in with this crashing with cost idea. And in this case, I think it is actually easier to utilize the table method, even though it might take you a little bit longer. So the first example that we've got here on page 47 is actually asking you to do it by inspection. So let's work through and see how we go. So to restore a vintage train, 13 activities need to be completed. The activity network below shows these 13 activities and their completion time in hours. So looking at the questions, firstly we need to find the earliest start time of F, the latest start time of L, and what is the float time of J. So in order to do that, let's do our forward and backward scan so that we've got all of that information. This one does get a little bit crowded. There's a lot going on. Okay, so starting at the beginning, A gives us 5, C plus 6 is 11, G plus 3 would be 14, and we'll check the other path, B would give us 5, but D, 5 and 2, 7. So moving forward with 7. 7 plus 4 for F is 11. J makes that 13. Coming back to E, so 7 plus 2, 9, plus 4 for H, 13, but we've got 14 as the largest value there, plus 7 for K, 21. L, 9 plus 3, 12. Let's go down and do I, so 9 plus 3, again 12, but 13 is larger, so 13 plus 6 for M, 18. 21 is our largest value there. So there's our completion time of 21. Working backwards from here, let's go K, so 21 minus 7, 14. 14 minus 3 for G, 11. Minus 6 for C, we've got 5, but we need to consider D as well. So let's go back to the finish, and 21 minus 3 for L, 18. We've also got H, so 14 minus 4, 10, but we also need I. So let's go back to the finish again. 21 minus 6 for M is 15. 15 minus 3, 12. The smallest of those values is 10, coming from H. 10 minus 2 for E, 8. Let's get the rest here. So at J, so 15 minus 2, 13. 13 minus 4 for F gives us 9. Smallest value going backwards is 8. So D, 8 minus 2, 6, but 5 is the smallest, which means A, 0. B, we've got 8 minus 5, 3. So B, 0. Just do a check. Yes, we've filled in all of those boxes. Our critical path goes A, C, G, K. That gives us our 21. So now answering those questions, the earliest start time for activity F. So looking at activity F, the earliest start time in green is 7, and this was in hours. The latest start time for activity L, so going back to L, and here this is where it's important to look at the value, the red value for L. So at the start of L, what was the number working backwards in the backward scan? It was 18. The float time for activity J, so activity J, 11 and 13. So our float time will be 13 minus 11, so 2. Continuing over the page, just before they started restoring the train, the members of the club needed to add another activity X to the project. Activity X will take 7 hours to complete. Activity X has no predecessors, but must be completed before activity G starts. So no predecessors mean it will begin at the start, because nothing has to happen before it, and then must be completed before activity G, so it must come into the vertex for the start of activity G. So what is the latest starting time of X if it is not to increase the minimum completion time of the project? So if we go back to our diagram, if we're to think about this edge, so it would start at the start and it would connect in at the start of G. So this would be X. The question is asking us, what is the latest starting time if it takes 7 hours so that it doesn't delay the completion time at all? Okay, so working backwards from here, yes, we would have a forward scan, we would have a 7 coming in, okay, but 11 would come still into the box, so that forward movement would still stay the same. Our latest starting time working backwards, so from the 11, the red 11, take 7. Going backwards, we would have 4. So our latest starting time, so that there is no delay, would be 4 hours. Okay, now moving on to some crashing. So activity A can be crashed by up to 4 hours at an additional cost of $90 per hour. This may reduce the minimum completion time of the project, including activity X. So it's including that additional edge. Determine the least cost of crashing activity A to give the greatest reduction in the minimum completion time of the project. So this means we may not want to reduce by all of those 4 hours. So it's similar to what we were doing with single activity, where we look at how much we reduce, but then think about, do I need to do the full 4-hour reduction? So if we're doing this by inspection, what that means, back in my diagram, I want to think about the impact that reducing activity A may have. So to make that a little easier, I've just cleared everything out so that we can just concentrate on the graph as it is. So you can do this over the top of your critical path that you've already identified, but it might just be easier to do onto a blank version. So remember, we're considering A and reducing that by up to 4 hours. So if we did reduce it by the full amount and made the time now 1, we can check what impact that has. And so in order to check that, we do need to redo our forward and backward scan. And remember, now we've got that additional activity X as part of the project. So again, a little bit time consuming, but it allows you to see clearly what we're doing. Okay, so oops, that should be a 7 moving forward, 7 coming in from X, they're both the same, 10 from G. If we go back and do B, so we've got 5, or we've got 3 from D, so 5, F gives us 9, J, I've got 11, or 10, so 11, M, 17, L, 10, and then let's finish off, so H, 11, so 11 moving forward, and 18, so 18. So we can see we have saved time. We've saved 3 hours. So it's cost us 4 hours. Let's see if that cost of 4 hours is needed. If it is, A will be on our critical path. So moving backwards, G, 11 minus 3 gives us 8. So moving from here, X would have late start time of 1. C, 8 minus 6, 2. And let's check the other options or the other paths. So H, 11 minus 4, 7. From L, 18 minus 3, 15. And M, 12. 12 minus 3 for I gives us 9. So smallest number going backwards, 7. Minus 2 from E, 5. 12 at the end of J, so minus 2, 10. Minus 4 for F, 6. So 5 moving backwards. 5 minus 2 for D, 3. So 2 in the box. 2 minus 1 from A leaves us with 1. And B gives us 0. So our new critical path is going through B, E, H, K, and 18. So we can see that A is not on the critical path. The other thing we can see is that A now has a float time of 1. So we've reduced it by 1 too many. And therefore, we can say A, we need to reduce by 3 only. Okay. It will then mean, so this is where we need to double check we're not throwing anything out. But what we should be able to do is go, well, instead of down to 1, it goes only down to 2, and check that little flow through, that we're not then causing any change to what the critical path would be. So basically just checking at the points where our pathways join back into the critical path, so at the vertices there, that it's not changing the value that we're going forward with in our forward scan, and it's not. So then we can safely say, yes, reduce A by 3, it's $90 per reduction, so it would cost us $270 to do. And that gives us a minimum completion time, a new completion time of 18 hours. So you can see there is a bit of work going backwards and forwards, and when there's multiple activities involved, it becomes really complicated. So that's where having a clear idea of what you're looking for is really helpful in this case.